All right, we finished with complements. So we're going to put a little reminder over here in the corner. The reminder was what? Probability of A or B is defined as probability of A plus probability of B minus probability of A and B. What was the one little thing about this end? In a single trial. In a single trial. So that was the important part. So that was addition. So today we're going to start doing multiplication rule. Multiplication rule. Multiplication rule. So let's start with notation. That's the notation for multiplication rule. Now, this is read as probability of A occurring and then B occurring. So multiplication rule says it's probability of A and B occurring where B occurs after A. So one after the other at the same time. Addition rule says at the same time. Multiplication says one after the other. All right, well, if we have this, let's look at, I'm going to hide the reminder for now. Let's look at an example. Let's say that this quiz for today looked differently. Let's say the quiz looked like this. We had two questions. Question one was Mr. N owns a Audi. And this is a true and false question. It's one of those, almost freebies if you're stalking me and impossible if you don't. And question two was Mr. N's favorite singer or my favorite band. And we had some choices. Why not? It could be a choice, kind of tripping you out. So I don't know. We have some choices. Now let's make it tricky. So we have NSYNC, Beyonce, Three Doors Down, Kazik, which is a Polish rapper, and Rammstein, which is a German death metal band. Well, it's not death metal, it's hard metal. Anyways, you have some choices, right? And let's say this quiz was like this. What are your chances of getting it right?
The first one.
Both of them. It's a whole quiz.
1 in 10.
You're saying 1 in 10. How did you get it?
Multiply 2 times the 5 options possible down below.
Okay. So what you're telling me, you said, hey, I'm going to split my choices for the first one. And I'm going to say, hey, I have A, B, C, D, and E, A, B, C, D, tree diagram, right? Because when you're saying 1 out of 10 means one
Out of 10.
event, right? One occurrence satisfies the event out of the sample space. So what is the sample space? The sample space, well, I answered true for the first question and I got A for the second one. Or I got true and B, or true and C, or true and D, or true and E, or false and A, and false and B, and false and C, and false and D, and false as E. Right? And here's my sample space. Right? Assuming that I don't have a metaphysical relationship with my car, that it is an Audi and it's not, right? I have just a little sticker saying Audi on a broken down, BMW. And I'm not an audiophile which completely is in love with 2 or 3 bands, right? Only one of those choices will work. One of them will be correct. So it's 1 out of a sample space of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the probability of getting this quiz right is truly 1 out of 10. Again, this example is relatively simple, but right, it's there to illustrate. Okay. Too easy. Let's crank it up a notch. Let's say that I'm going to go back to my courtroom and I had this chart on Monday, 11, 72, 85, and 9. Okay, so let's take a look at this. Let's look at probability to select someone who is guilty and then selecting someone who is not guilty. What's the probability of selecting someone who is guilty and then selecting someone who is not guilty? All right, let's try the probability of guilty. What's the probability of selecting somebody who's guilty? Well, I suppose we should start with how many people are in this courtroom. Right? And then how many people are guilty? 83. Well, that was easy. All right. So probability of not guilty. Not guilty. But that's and then not guilty. So and then not guilty. So that's probability of selecting somebody who's not guilty. Okay, not guilty is 85 plus 9, 94. And what's on the bottom? No, because we selected somebody who is guilty already. Lynch mob runs into a courtroom. right? What are the chances that the second person they hang is not guilty, right? They hanged already somebody, so yeah, right? We took one person out. So the difference between this and this, right, starts to appear. Here, regardless of which one I choose for the first one, I can choose whichever one I want for the second one and still get the same probabilities. Here, I run into some trouble. Suddenly, things are starting to change with time. Okay. If you look at this from terms of just a sample, you don't look at it as a courtroom full of people, but just a sample or a population that you put. This is called without replacement. Okay. All right, so what we are starting to notice that one is affecting the other. And so we should probably start looking at conditional probability. It's the probability of an event occurring right, and we have two examples here. Probability of getting the second question right, given that you got the first question right or wrong, right? Probability of finding somebody not guilty, given that you already found somebody who's guilty out of a crowd, right? This is affected by this. This is not affected by this. All right, we have a notation for this, so that's P, vertical line A. And we read this as follows. This is the probability of event B occurring given that event A has given that event A has already occurred. Okay, so example. What are the chances your partner, assuming you're dating or you're, married or something, your partner will call you this second or, within the next half an hour and tell you you're breaking up? Slim, I would say, right? Most of you, I'm assuming, have no excessive drama in your life, so there's slim chance. What are the chances that your partner breaking up with you if they found out you've been cheating on them?
It's like a 50-50.
50-50, right? Great. No, right? So you have two events that are conditional, right? And the breakup is conditioned based on what happened before, right? Most of the beautiful comedies are designed because you tripped, you slipped on a banana, you hit the piano, the 50-pound weight fell on your head, right? And you just kind of postponed. If we just removed one of those events, nothing else would happen, right? The domino effect. This is talking about a domino. What are the chances of the second block falling, given that the first block fell? Right? If they're independent, you have two dominoes standing side by side, you tipped over one, the second one won't be going anywhere. At least it shouldn't. Right? And so we should probably discuss things that aren't affected by each other, and we're going to look at independent events. Well, independent events are the occurrence of one event does not So occurrence of one event does not affect the occurrence of another event. Example?
Sun and the moon?
How?
But the moon is not dependent on the sun to come up,
The sun has
but
to
it does come up.
Sure. In a simplified term, sure. But on the other hand, we observe what we see. If we have a lunar eclipse, right, we won't see the moon.
Yeah.
So right, but sure, they are rotating independent, as far as we can tell, independent of each other. Great. How about winning one poker hand versus another poker hand, just by cards alone, right? The chances of you drawing two aces the first hand and throwing two aces in your second hand are the same, right? That's independent of each other. That's an example. Getting a 4 on one quiz doesn't guarantee you a 4 or increase or decrease your chances of getting a 4 on another quiz, right? Those are independent events. But there are events that are dependent, right? You cheat, you'll get broken up. You run a red light, your chances of accidents grow up, right? You have a gun, your chances of getting shot with your own gun get higher, right? Statistics. Although I think the youngest killing spree was performed by a 2-year-old with 4 people dead. So America holds the candle to that. Sorry? 2-year-old? 2-year-old or 3-year-old? I think they got kind of a automatic on the bed and they decided to spray uncles with bullets. Smart kid. All right. So let's note something. So note. If A and B are independent, let's say A and B are independent, then what happens to probability of B given that A already happened? Right? This says probability of B given that A already happened. If event B is independent of event A, aka event B doesn't really care about event A. What happens with B is not influenced by event A. What is this turning into B?
The probability of B.
Yes, exactly. If A doesn't matter, then it doesn't matter if it happened or not. We don't care. So if A and B are independent, then probability of B given that A happened is the same as probability of B. Right? If we consider event A sunset, event B sunrise, those are independent events. Sunsets are occurring every day, right? And sunrises are occurring every day. Then we look in the morning, we are getting a sunrise. We don't care if it was a sunset or not. This morning we're going to get a sunrise. Right? So that's the type of connection. Okay, so let's do some examples. So let's do the first one. Let's do roll a die. Roll of a die, and we have a probability of 5 given that 3. What's that? Well, we roll a die, and we have this. How do we read this?
Probability of 5
And no, not n3.
because of 3.
Given that 3 already happened. This means I'm going to roll the die. I got a 3 on my first roll, and I'm going to roll again. I'm going to ask you if this is going to, right? What's the probability of rolling a 5? So you have a die. You roll the die. You get a 3. You roll it again, and what's the probability of getting a 5? 1 out of 6, right? Because rolling a 3 and rolling a 5 is independent. So that's probability of rolling a 5, which is 1 out of 6. Okay, let's complicate things. Let's say we draw cards. Draw cards. Draw cards. And let's say you have a probability of queen given that 9, and probability of queen given that 9. So let's call this one with replacement and without replacement. Again, replacement means I took the card out, I showed it to everybody, I put it back in the deck. That's what replacement means. It's a magician thing. So the first one says what? I'm asking you what the probability of pulling a queen out of a deck of cards is, given that I just pulled a 9, and I put the 9 back in, right? I replaced the 9. So I had a deck of cards, I pulled a 9, everybody's happy, put it back, pulled a queen. So what's the probability? 1? 4. There's 4 queens. So that's 4 out of 52. How about the second one? Second one says, hey, I pulled a 9, showed it to everybody, put it on the table, and now I'm pulling a queen. 4 out of 51. Is everybody comfortable with this description? Yes? Good. All right, so if you guys are so smart, let's crank it up even more. Why not? You know? Well, it's statistics, and I'm teaching decision making. I'm going to have to make some assumptions. All right, let's do those. With replacement, let's go probability of, and without replacement, and then with replacement, and without replacement. So with replacement, probability of drawing a king, given that you drew a king, and without replacement, probability of drawing a king, given that you just drew a king, and then with replacement and without replacement, heart, given that you drew a 3 of spades. First one. 4 out of 52, right? I pulled a king, got lucky, I shoved it back in the deck. I'm trying to do it again. There's 4 kings, the whole deck is there. How about the second one? Well, I pulled a king, I put it aside, so there's only 3 kings left in the deck, and there's 51 cards left in the deck because I pulled a card that is a king. Okay. Heart, given that I pulled 3 of spades. Sorry? Out of? Yep. And the second one? 12? 13 out of 51.
Oh,
Without replacement, but I pulled a 3 of spades. I pulled a 3 of spades, I put it on the table, and the question is how are the chances of pulling a heart?
okay. No, so if you pull the 3 of hearts, then it would be 12 out of 51.
If this was 3 of hearts, this is 3 of spades.
I know, but if it was a heart.
So if it was probability of a heart, given that we pulled a 3 of heart, without replacement, that will be 12 out of 51. Because I pulled a heart and a card out of the deck. Okay. So far, so good. All right, so let's start erasing stuff. Save this part. So multiplication rule. So multiplication rule has, in most textbooks, it has 2 formulas. There's 2 formulas for multiplication rule. I'm going to give you one. I'm going to show you how to get the other one because that's relatively easy to do. So what is the first one? Well, the first one says, hey, I'm going to take the probability of event A times probability of event B given that A already happened. Right? If you take a look at how we read this as probability of A and then B. Yes? That's how we read it. So probability of A and then B, but A already happened. So this is how multiplication looks like. Now, if A and B are independent, then probability of B given that A already happened equals to probability of B. Right? If A and B don't influence each other, then regardless if A happened or not, B is still going to be the exact same thing. So that's that. Thus, the multiplication rule turns into that. So if A and B are independent, you get this. But if you know this and how to operate this and you remember this follows. No?
No.
Yes. Okay. All right. So let's have some fun. Let's look at something called Mr. N's bag of marbles. Mr. N's bag of marbles has the following marbles. Has 3 red marbles, 2 yellow marbles, and 4 blue marbles. And we're looking for the following. we're looking for blue and then a yellow. Probability of blue and then yellow. One is with replacement, the other one's without replacement. Then we probability of red and then red. And then probability of yellow and then yellow and then yellow. Yellow submarine, yellow submarine. So how do we do the first one? We're going to do it exactly this way. So that's probability of blue times probability of yellow, given that blue already happened. Yes? So here is the question, what this replacement does. So what does the procedure look like? We take the bug, right? We pull up blue, right? And then we pull it back, right? And then we pull up yellow. Does it matter which marble we pulled out first? No, because we replaced it right after. So this really becomes probability of blue times probability of yellow. So in our case, probability of blue is what? 4 out of 9. And probability of yellow is 2 out of 9. And here's a question where almost half of my classes get wrong. What is that number if you multiply those two fractions together?
6 and 9. Oh, 6 and 18 is 1/3.
8 out of 16, 8 out of 9, and I'm going to start judging you people. What is that number? What's 4 over 9 times 2 over 9? 6 over 81. This is like the third answer, and you got all. So let me get this straight. This is somewhere between 6 over 81 or 8 over 9 or what was the other? 8 over 18? 6 over 18. Thank you. There's hope afterwards. Close. So close. Please, it's a multiplication fraction. We multiply the top, we multiply the bottom. It's a 300 level math class. Let's leave it at that. Okay, second one. Without replacement. If we do without replacement, we go probability of blue, which is still 4 out of 9. Nothing changed. But now we're going to pull up a yellow. There's two yellows, but the bag of marbles lost a marble. So 2 out of 8. And we multiply that and we get
72.
I don't know what we get, but I get a heart attack. Okay. So far so good? All right. How about the two reds?
Without replacement,
Without replacement.
3 out of 9.
3 out of 9
2 out of 8.
and 2 out of 8. Right? We pulled out a marble, we lost a red, and we lost a marble. And that's okay. Good. The hope is slowly getting restored. And then let's do the last one. Yellow, and then yellow, and then yellow. Not possible. Not possible. You obviously haven't worked for the government balancing the budget. It's definitely possible. So let's look at first yellow. 2 out of 9. Second yellow. 1 out of 9. Third yellow. Well, you guys are almost right. It's 2 out of 9, 1 out of 8, and 0 out of 7. Because we lose that marble. Well, let's say 2 times 1 times 0, 0, and then 9 times 8 times 7. Well, 0. Yes, it is impossible. So the probability for that is impossible. But here's the proof it. Right? You won't be able to prove it to me unless you actually drag every single marble out of my bag. Just. But here's the mathematics, you can prove that it's 0. Okay, that was easy. Let's up the ante again. Let's make it more difficult. Alright, just in case you wonder what the math is good for, because that question comes up a lot in all my classes, like why do you use math? How many of you play poker? Excellent. What's the highest non-flush card set? As an upper straight? Upper straights are pretty good, right?
No, you said highest?
Well, it's pretty high. Upper straight?
Royal flush.
Oh, royal flush. We're going to get to royal flush in a second. Upper straight is what? An ace, a king, a queen, a jack, and a 10.
Essentially.
Oh, we're going to get to that in a second. Let's do this first. So let's say we are down to cards. What are the chances we're going to get an ace? What are the chances of we going to get a king after we pulled an ace? So what I'm looking for is probability of ace and king and queen and jack and 10.
In that order? Or
Sure, why not? It doesn't matter. Right, so it's 4, 51, and then 4 out of 50, and then 4 out of 49, and then finally 4 out of 48. For people that are wondering how bad that is, that's going to be pretty hard to pull. What is it? 4, 4, 4, 4, 4. 10, 24 divided by, I'm going to, 300. You're probably right. It sounds about right, but 50 times 51 times 52 times 49 times 48. Yep, you're right. Three, 7, 5, 2, 0, 0. Yeah, 312 million. Easy, right? 1,000 on top, we take 1,000. It's 1 in 312,000. And I take my chances. The chances of you pulling a royal flush is 1 in 312 million.
straight flush.
Yeah. Royal flush. Fun, right? So just in case you wonder what math is good for, especially statistics, poker. There's things you can do with this knowledge. Sorry?
I play go professional poker.
I don't know what that is. Okay. All right. When we talk about complements, right, we talk about complements as this everything but part, right? Complement of A is everything but A.
Oh,
Yes, question?
question. So that's a royal flush. I mean,
No, that's just some ace, some king, some.
so your
This-
flush should be different then.
Royal flush will be this.
Yeah, one. Okay.
You were getting your hopes up, right? So, don't get your hopes up. It's really bad. So we talked about complements as being one of the opposites, right? And that's very nice. We have this statement we commonly use of at least one. You heard that statement before? Right? At least one rotten egg in the fridge. is enough, right? At least one. What does at least one mean?
Event of
One or more, right? Think about, for the people that are over 21, think about you go to a bar and you're going to have at least one beer, right? It means one or more. So what's the complement of this? What's the complement? So what's the complement of at least one?
1 plus.
1 plus is at least one, means 1 plus.
None.
None, right? At least you go to a bar and say, hey, I'm going to have at least one beer. Right? If you have my genetics and my size, that could mean one beer, could mean 2, could mean 3, could mean 4, could mean 5, could mean 6, could mean 7, could mean 8, and this is where I start thinking about calling a cab, right? Or could mean 9. 9 beers, right? Realistically, I usually cannot afford 10 beers in a row. But you don't know. So if you were starting to talk about probabilities, what's the probability of me having at least one beer? That's probability of having one beer, plus probability of having 2 beers, plus probability of having 3 beers, plus probability of 4, plus 5, plus 6, plus 7, plus 8, plus 9. It's a lot of calculating, right? Just to describe this large set from 1 upwards.
one or greater.
One or greater. Well, but if the complement of at least one is none, right? So the probability of at least 1 equals to 1 minus probability of none. Right? Because it's either event A or everything but event A. Right? At least 1 and none combined together give you 100%. There's no other options. You either have no beers or you have 1 or more.
So none would be 0 in some case.
In this case, it would be 0, yes. Right? So either I have a 0 beers or I have 1 and more. 2 sips doesn't count. Right? Right? So would be easier to take a look at probability of having at least one beer as 1 minus the probability of not having any. Right? We did the complements. This is very familiar to the probability of A equals to 1 minus probability of complement of A. All right, so let's take a look at what it could be used for. Let's say we flip a coin 3 times. Can we do that? Easy, right? And I'm on the probability of at least 1 head. Well, probability of at least 1 head means what? Well, it means probability of 1 head plus probability of 2 heads plus probability of 3 heads. Yes? So far everybody's in agreement.
Why can't it be probability of 1 tail and 1 tail? Is that not a complement of 1 head?
Of 1 head, I could have 2 tails, yes. But let's deal with this for now like this. So how did we deal with probabilities? We created the sample space. So let's create the sample space. And either by tree diagram or any other way. There's your sample space. Head, 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 tail, tail, head, tail, head, tail, tail, head, tail, head, tail, head, tail, tail, and tail, tail, tail. So that's the sample space. So let's take a look. One head. Right? Those are 3 options. Out of how many? Out of 8. Right? Our sample space is size 8. 2 heads. It's right here. So that's 3 out of 8. And then 3 heads. Right here. And that's 1 out of 8. And we come out to the probability of at least one head to be 7 out of 8. Everybody happy with this? Yes, I hope so. So let's look at this way, the other way. Probability of at least one head equals to 1 minus probability of none, right? At least and none are complements. Well, what does it mean none? Means 1 minus probability of no heads. Well, what does it mean to be no heads? If it's a coin, if it's no heads, then it's all tails. In our case, that means probability of tail and tail and tail. Right, we have 3 flips, so it's going to be tail and then going to be tail. Are those independent events? Yes, flipping a coin is independent. One flip doesn't affect the other. So that would come out to be 1 minus probability of the first tail is 1/2 times probability of the second tail is 1/2 and third one is 1/2. So that would be 1 minus 1/8, which is 7 over 8. One minus 1. Right. 1 times probability of a tail times probability of a tail times probability of a tail. Because they're all independent of each other. Okay. Well, in this case, this seems faster than this. A lot faster. Yeah? Okay. In that case, we should probably make it more difficult. How about this? Flip a coin 20 times. Probability of at least one head. Now this will be fun because the sample space will be over 1 million simple events, which is fun. No? No. So if we have 20 flips, which is again not a very large set. 20 flips isn't exactly life-altering amount. This becomes ridiculous. This method becomes ridiculous. Let's try this one. So, probability of at least one head equals 1 minus probability of none, which is 1 minus probability of all tails, which is 1 minus probability of tail and tail and tail, which is 1 minus 1/2 times 1/2 times 1/2. How many of those 1/2s are there? 20. We flipped the coin 20 times. So that comes out to be 1 minus 1/2 to the 20th, which for people that keep score, it's 1 minus 1 over. Take it right. 148. Oh, there's a 5. 576. And since I know you guys are so keen on percentages, this comes out to be 99.9999046%. So the probability that you flip a coin 20 times and you don't get a single head is really, really small. Probability of getting at least one head is this. 99.9999046%. So if somebody bets you that they have the magic coin and magic touch and they're going to flip the coin and not get a single head, bet them big. Wreck really big. Okay, that was easy. Eh, 18 minutes. I can do great things in 18 minutes. Okay. Any questions about anything so far? Okay. Just a heads up, I really like those kind of bag of marbles type of questions. I'm not saying anything, I'm just saying. I haven't lost a marble since like 3rd grade, so I'm good. All right. All right, so this is just a mention. This is not something that's going to be tested, but I think it's worthwhile noting is that when you have conditional probability, which is defined as we can find conditional probability from this. How did I got this? I got this from here. The bottom is the multiplication rule, right? So if I divide by probability of A, I get the conditional probability. So probability of B, given that A already happened, is the probability of A and then B happening divided by probability of A. So just in case you need to find conditional probability for a project, assignment, work, this is how you do it. In the couple years I've been teaching statistics, this kind of problem hasn't shown up on my exams. But I'm just letting you know that you can calculate this. A lot of the times you're going to be given this, but you can calculate this. So just a heads up. All right. All right, now let's continue. We're going to go back to the courtroom.
the example of conditional probability?
Which one? No, this is conditional probability. This is a separate, just a little mention like, hey, this is how you can get it just in case you need it. Because sometimes people have questions about conditional probability. What are the chances of the car catching on fire if the tank breaks? Well, we have a statistics for tank breakings and then fires, right? Because that's the statistics we can get from DOT. And we have the probability of the tanks breaking. So this will give us probability of catching fire given the tank broke, right? So you can have a statistic saying, hey, this is how much risk you're adding to the insurance, for example, or to the calculations, to the model. So it's another tool to use it, right? Because a lot of us look at this as just a probabilities, but those are numbers. Those numbers can be moved around and they have a meaning. So if you have probability of, so let's say event A is tank failure and event B is catching fire.
So you actually compounding the.
Yeah, I can create the conditional, right, the compounded probability here, the conditional probability. If I have probability of tank failure and then catching fire, right? So you look at burned down cars and be like, hey, they had the ruptured tanks. You have that statistic. You can have this statistics from the manufacturer, right? Which means you can calculate the statistics of a car catching fire given the tank already broke. It's an insurance thing that I've seen it at. That's the only example I can think of. Flooding in a flooding zone, right? We know how many houses are flooded when they are built in flooding zones, right? And we know how often the floods happen, the probability of flood happening. So the question of what's the probability of house getting flooded given that it's built in a flooding zone? That's the only place where I've seen examples of this being used in real life that don't get past a certain level of complication. All right. So let's look at this. Let's look at those. Probability of guilty given that he did it, or she did it, or they did it, and probability of that they did it given that they were found guilty. So how do we do it? Hang on, let's look at this one first. What place are we looking at? What happened first? They did it or they were found guilty? Did it. So we're looking at specifically this, right? So how many people are guilty?
81. Oh, you did it.
72.
72, because I'm just looking at the guilty people. So that's 72 out of 81. Right? We already picked the did it part. Now we're looking at guilty given that they did it. Right? So I'm just looking. All right, second example. What happened first? Well, first guilty happened. So this happened first. So how many people did it? 72 out of. It matters which way you put it. What's the difference between those two? This is our court system, right? You do it, and then you're found guilty. This is a lynch mob. We presume you're guilty, right? We presume you did it by already finding you guilty, right? Did it, we found you guilty, and then we assume you did it, kind of thing. Right? That's the difference. Law and lynch mob, and they give you different percentages. Those things are not interchangeable. Conditional probability you cannot flip around. You might get lucky. You might get lucky, but so question, how do I do it? Again, this says guilty given that did it. So I'm just looking at the column that did it, or the row that says did it, and I pick the guilty out of it. So I just look at this. For the first one, I'm interested in this. And I pick the guilty out of this column. Second one says, hey, I'm looking at guilty and only guilty people, that row, and I'm going to pick the people that did it. So these people out of this row. Right? So remember the quiz, you had that little table? I could say, what's the probability of picking a freshman given that they are driving a car? And then you just look at driving a car row and you pick just the freshman. Should I do another example of this? Yeah, okay. All right, so.
But I had a question though for you.
Sorry?
I had a question before you.
Uh-huh. Shoot.
Sorry. So if it was the other way around, saying they didn't do it, it would be 11 over 8.
So, okay, so let's do it. Probability of didn't do it, given that they're guilty, let's say. Or probability of didn't do it, given that not guilty, I suppose. So if you look at this one, right, we're looking at guilty. Given that you're guilty, which is just this, you didn't do it, 11 out of 83. Second one, given that you're not guilty, so given this little section, you didn't do it, 85 out of 94. Right? So this specifies which column or row you're looking at, and this which cell or cells you're looking at.